Hello and welcome. This is SFU Math 152, Calculus 2. Name's Brenda Davison. We are going to cover this time section 8.2, the area of a surface of revolution. So we've already covered the volumes of revolution. So now we're going to look at those same solids that we make by revolving something around a straight line. And we're going to ask not what the volume of that thing is, but what the surface area of it is. And the reason we're doing this now and not when we did the volume is because we need the arc length in order to do that. Okay, I love this quote. Mathematics is no more computation than typing is literature. So I want you to, as you're learning new things, I want you to not, you do know, if you're going to write a book, I suppose you do need to know how to type. But of course, that is only a very small fraction of where you want to be in order to write a work of literature. In the same way, you need to be developing these skills, and you definitely need to know how to do these sort of things. But you want to be moving now, especially to thinking of the problem solving things, of the structure that you're learning, of the critical thinking skills. Like you want to be moving in that direction, not just focused on the computation. Okay, so what we're going to do, we're going to learn how to do something here. We're going to learn how to do a certain type of computation. We're going to learn how to figure out what the surface area of a solid of revolution is. Okay, so here's an example to start us off. We're going to try to find the surface area of a paraboloid, which is obtained by revolving the parabolic arc y equals square root x between 0 and 2 about the x-axis. Okay, so that dark blue line there is going to go around the x-axis, and we are going to get a solid, and the solid is going to look somewhat like this. We're going to go around the x-axis, and it's going to come in here, and so it's look like this. So just a couple of those circular cross sections that we see on these types of solids, and that is what is called a paraboloid. And so let's take a look at one of these circles here. I'm just going to make it a little bit bigger so I can draw on it. And so what do we see, for example, here, this circle here that is sitting in there, the circumference of that circle, well, let's look here, is its radius. That the radius there is y. So the circumference here is 2 pi times y. And then if we were going to take a look at the arc length of what we've got happening here, let me just pick a different color so we can see that. I would then take a look here at this arc length, and we know how to calculate that arc length, that we would be adding up these 1 plus f prime at x squared dx. So that arc length would be the integral there. So that actually, when you think about it, we're taking that arc, and that arc is going around the x-axis, and that is giving us that surface area. Okay, so we are going to take a smooth curve, C, given by y equals f of x, and then when we revolve it around the x-axis, the surface area is the circumference. That is 2 times pi times y. Y is f of x. And then we have the arc length. And so that is going to be the surface area. We're going to add up all those little pieces. And if we go around the y-axis, then the circumference is going to be 2 pi x, and then there's our arc length. Okay, so we have to be careful when we're doing this to think about where is the circumference of that circle. Let's go back here and imagine if we were going to go around the y-axis. So if we were going to go around here like that, then we would be forming a surface that looked like this. Our circles, our cross-sectional circles would be there, and the circumference of this thing here would be equal to 2 pi x. Okay, so the circumference is different depending on which way. If we go around the x-axis, we get this circumference. If we go around the y-axis, we get this circumference. But the arc length is the same. So that is why we have these two different formula here. We have around the x-axis and around the y-axis. So of course you can either memorize these, or you could just quickly draw yourself a diagram and say to yourself, where is the circumference of the circle and how would I calculate that? And then you would be able to regenerate that. So we're thinking about the arc as being made up as straight lines, and we rotate those straight lines, and each piece results in a little frustum of a cone, looking like that. Little frustum of a cone, like that. And we can calculate the surface area of that little frustum of a cone, and then we let the number of divisions of the line become infinite. That is just like we did with the arc length, and we get the the formulas here for the area of a surface of revolution. Okay, so let us take a look here. I'm going to have to erase some of this stuff here. Hang on a second. I see I've got a bit of a issue here. Hang on. Nope, I don't. Just a little bit. Okay, sorry about that. Okay, so here we've got the area formulas for the surface of revolution. So yeah, we have well, we saw two possibilities earlier, and that was we had the case earlier, y equals f of x. We had y equals square root x, and then we revolved it about the x-axis, and then there it was the circumference, and we revolved it about the y-axis, and there's your circumference. We have also, of course, the other possibility that we are given a function in this format here, x equals g of y, and then we're going to integrate in the y direction rather than in the x direction, and we have the same issue. We just have to identify how we're computing the circumference. So there's two possibilities. So there's four possibilities all in all, because there's how are we going to calculate the circumference if we're revolving about the x-axis or the y-axis, and what are we integrating with respect to x or with respect to y. So in both of these cases, going about the x-axis, this is 2 pi y. But in this case, we're integrating with respect to x, and y is equal to f of x. In this case, we're rotating about the y-axis, and so the circumference is 2 pi x, and x is g of y. So just this has to match with this. Okay. I don't know what else I want to say about that. Maybe I'll just draw a couple of pictures, try to emphasize what I'm saying above here. So we've got this condition here, y equals f of x. We go about the x-axis, and it looks like this. And our radius is equal to f of x. Okay, when we have the corresponding condition here where we take our function and we go about the y-axis, that is this one like that, and we have our cross-sectional circles there, and here in this one our radius is equal to x. That's the radius right there, and here's the radius right here. Okay, then this is the condition. These two conditions is when we have identified y as f of x. Okay. And we have the other two conditions. This is where we have indicated something, perhaps looking like this. X equals g of y. We have some x as identified as a function of y. We rotate about the x-axis, and we get something that looks like this. And what is our radius right there of that circle? That's a fairly unusual looking circle, but it is supposed to be a circle nonetheless. That radius right there is equal to y, y being f of x, but in this case we do not have y as a function of x, we have x as a function of y. Okay, and then the other case, the fourth case, is this one here, where we have the same curve we've had in that last one, x equals g of y, and we are revolving here about the y-axis, and we get a bowl-shaped thing that we're wanting to find the surface area of, we've got a circle in here like that. That circle has a radius, and that radius is x, and x is g of y. So this radius here is g of y. Recommendation, like I've been doing many times, stop the video right now. Recognize the four scenarios, kind of basically form this table for yourself, and then don't have these like this. Write the table out, don't have these, and then attempt to put the right formula in each box, and then take a look, undo these, take off the scribbling, and then take a look at the table, look back and say, can I do this right? Because then you won't have any trouble doing that. And you can oftentimes draw a picture, and that picture makes it much clearer which one of the formula you are using. Okay, so let's take a few examples of this. I mean, now that we've developed the formula, it's really there's really not much else to say. It's like we've already gone through how to find volume of revolution of a solid formed by revolution, and then we've gone through how to find arc length, and now all we're doing is putting a couple of these ideas together, and we are saying this is how we find surface area. Here's a few examples of how to do it, and that's all. And then for you there's some practice, but this is not there's really not a whole lot else to say about this. Nothing sort of deep underlying thing I can add to this. Okay, so here we're going to try to just see how to make this work. And we've got a function here, y. So we've got y equals f of x for part A, y equals square root x, and x is going to go between 0 and 2, and we're going to rotate about the x-axis. Okay, and then we're asking, what is the surface area? And this is the original problem that we encountered, and we get the paraboloid. Okay, so that is, we have this here, we're going around the x-axis. And so we have a situation that looks like this. And we've got a radius here. Radius is equal to f of x, and that is equal to the square root of x in this case. And this shape, I said earlier, this is a paraboloid, and this is a shape that is extremely important. Where do we see this? And why? Okay, so let me answer that, because you are not here to answer it for me. That is, these are when we see the satellite dishes. So these are all parabolic, the satellite dishes you see for television reception sitting on people's homes. So you see a dish sitting on their homes, and the cross section of the dish looks like that. And then that's sitting on their roof on some sort of a stand, typically, and then you see a little thing sitting up in the middle, and then there's a little thing like that. And so the reason that and these are paraboloids, so this is a two-dimensional cross section of the paraboloid. It's a parabola, and the reason why that is why they're parabolic is because we have incoming what are effectively parallel rays coming in the television signal that you wish to watch, and the parabola has the important feature that every line that parallel lines coming in reflect, and they all reflect to the same spot. Okay, so parallel is coming in, reflect, and that is where they put the feed. That is the pickup that brings the signal into your house. Okay, so if you have the transmitter is far enough away to make the assumption that we have parallel lines of signal coming in, and then the parabola has the highly important feature that all of those reflect to the same spot, and that is where you pick up a strong signal, and you bring that in, and you can listen and watch whatever it is that you're interested in watching. So this is the paraboloid is a really important shape for that reason. Okay, so we've got this thing here. So now we want to figure out what the surface area of our paraboloid is. So I'm going to use capital S for the surface area. So I'm going to take the integral. Oh, let me write out the general formula. I'm going to use this one here, 2 pi f of x, and then the arc length differential, 1 plus f prime at x squared dx. Okay, in this case, part A, the question I'm doing right now, I've got that A equals 0, B is equal to 2, and f prime at x is the derivative of square root x, and that is 1 over 2 root x. And so f prime at x squared is 1 over 4x. Okay, so I can now write out for part A what is the surface area of that paraboloid, and it's going to be the integral from 0 to 2 of 2 pi square root x times the square root of 1 plus 1 over 4x dx. It's looking perhaps a bit desperate, but it's not as desperate as it really is, okay, as it really looks right now. And the thing to do right here is to make a common denominator and add these two things together. So now there's algebra. We're making a common denominator. I don't like having 1 plus 1 over 4x. I'm going to make a common denominator of 4x. And then I'm actually going to see that 4x is square root 2 times the square root of x. So there's algebra, and I'm using this fact. 4x is equal to 2 times root x squared, which means, of course, I can factor that out. And I will do that. So I will be able to do a bunch of algebra here in order to simplify this. So check. Do this yourself. Check this yourself. Stop the video. See how much you can algebraically simplify. So the idea is to simplify here. You want to simplify the integrand. And so I haven't integrated or anything yet, and I've already managed to make this thing look much nicer. So this is algebra 4x plus 1 dx. That is much nicer. It's interesting. I think the like if I wind back here, I look at these and I think, oh no, like these are going to be, we saw already the arc length integrals, sometimes very difficult to integrate. And this looks even worse in some ways because we've got this arc length differential, and then we've also going to be multiplying by other things here. It looks like, oh no, but actually just as a result of, I don't know, just the way the squaring of this and then this being here, oftentimes the surface area integrals actually come out to be easier to evaluate than the arc length ones. And here's an example of that. Okay, so I've got this integral. This is now a straightforward to integrate. That's going to be pi times 2/3 times 4x plus 1 to the 3/2 multiplied by 1/4. Okay, so I integrate. Again, always be checking your integrals by quickly differentiating in your head, seeing have I got the constants right that I need to put in, because it's easy to make a mistake. Okay, and I'm going to evaluate that at 0 and 2, and then I will get pi by 6. I get 9 to the 3/2 minus 1 to the 3/2. And I can simplify that even further. 9 to the 3/2 is 27. 1 to the 3/2 is 1. So that 27 minus 1 is 26. So S will be 26 pi. 26 pi by 6. And that I can simplify to 13 pi by 3. Okay, so that is the surface area of the paraboloid. So that is if we were going to paint the outside of the paraboloid and we went down to the store, we would buy that many square liters, or square, what would we say, actually not square liters, so it's silly, square meters of paint. Okay, let's try B. Well, we've got y equals x cubed, and we're going to rotate about which axis? We're going to rotate. So this is similar to the last one. We're going to rotate about the x-axis. Okay, so it's going to be the same surface area expression. It's going to be the integral from, we're again going from 0 to 2, and it's going to be 2 pi f of x, which is x cubed, times the square root of 1 plus, okay, we got it. We know that f of x is x cubed. Then we need f prime of x. That is going to be 3x squared. Then I'm going to square that, and I'm going to get 9x to the 4 dx. Okay, maybe a little picture of what this one looks like. Cubic function like that. It's being rotated this way about the x-axis, so looks like that. And we have our radius here, and that radius is y, which is f of x, which is x cubed. Okay, nice situation happens. You see this thing is the derivative of this thing effectively. So this integral is much easier to deal with. We saw that when we tried to calculate the arc length of this function between, I forgot what, maybe even if it was between 0 and 2, it doesn't matter, whatever. We tried to calculate the arc length of this in the last lecture, and we got an integral that doesn't integrate in terms of elementary functions. So that does not happen here. We can calculate the surface area. Okay, so I'm going to do that using a substitution. That's going to be let u be 1 plus 9x to the 4, and then du will be 36x cubed dx. And so I'll have that du over 18 is 2x cubed dx. So I can replace the 2, the x cubed, and the dx with du over 18. So this integral will be equal to, the pi is still there. Then I'm doing a substitution. When x is 0, u is 1. And when x is 2, 2 to the 4 is, so this, and now I'm saying, I have to do a bit of a calculation. When x is 2, u is 1 plus 9 times 2 to the 4, that's 16. 9 times 16 plus 1, that is 145. So the integral is going to go from 1 to 145 of du over 18 square root u. And then that now the problem is pretty much done, isn't it? We can easily integrate that. That is going to be pi over 18 2/3 u to the 3/2 evaluated at 1 and 145. And I get a number out of that, which is approximately 203.44. Let me, in fact, I have the exact thing. I can do the exact thing here. That would be pi over 27 times 145 to the 3/2 minus 1 there. Okay, and that's that number there. Okay, I'm going to do C. I see that I've not left myself enough room here, so I'm going to scroll down. I'll come back to this area of the torus problem, but let me just scroll down a little bit, get myself a little bit of space, and I'm just going to do part C of these examples that I have here. This is one where we're going to use one of the other of the 4 formula that we've written there, so let's try it out. Rewrite the question here so we can see what it is. And that is, see, we have y is equal to x squared, and x is going to be between 0 and square root 2, and we're going to rotate about the y-axis. Okay, so we're y equals x squared, so this is this way, and we're going this way, so the looks like this here, like that. Okay, so our radius is x. So our surface area integral is going to be the integral from 0 to square root 2, and our radius is x, and then we have 1 plus f prime at x squared. F prime at x is 2x, and then we're going to square that. Okay, again, in terms of testing, oftentimes we tend to ask questions like set up but do not evaluate the integral for computing the surface area of this, or set up but do not evaluate the integral for the arc length. So oftentimes this is really the problem is understanding what integral it is that you want to evaluate. We're not going to put quite as much emphasis on evaluating these integrals. Okay. Let's go ahead and make some headway on that. Square root 2, and then we're going to have 2 pi x dx, and I have here 4x squared. So I've got 2 pi x 1 plus 4x squared dx. And you'll notice that nice thing happened again, where I have this sitting here, and then I see the derivative of it there. That makes this thing very simple to evaluate. I can do this with a simple substitution like I did the last one. I get u equals 1 plus 4x squared. I let u equal 1 plus 4x squared. That's what's underneath there. And then I see that du will be 8x dx. And I see that I've got 2x dx there, so I'll write that as du over 4 equals 2x dx. And then I can replace this 2, the x, the dx. I can replace that by du over 4. And I also have to, this right here is x is equal, so I'm making substitution. I must change the limits of integration. So I'm thinking, okay, when x is 0, I'm using this, going to be used here. And I'm looking here, when x is 0, what is u? Well, I put in x equals 0, and I find out that u is 1. And then when x is equal to root 2, I put that in here, and I see that root 2 squared is 2. 2 times 4 is 8. 8 plus 1 is 9. Please do not forget to change the limits of integration when you make a substitution on a definite integral. Okay, there's a pi. Let's put that there. And then I've got square root u, and I've got here du over 4. I mean, this is basically identical to the last problem. So that is 2 pi by 3 u to the 3/2 evaluated at 1 and 9. And I get here 13 pi by 3. Okay, actually it's the same problem as A, right? We just, it's oriented in a different way. Okay, so a few examples of how to do that. I mean, our Stewart textbook has lots of nice problems. I highly recommend, well, of course, if you're in my course right now, I'll be assigning some of them for you to do. But, it's pretty easy. Just turn to the section 8.2 on surface area. Go ahead and do, I don't know, some number of them, 10 or 15 of them, and then you'll have how to do that in your head, and then that's a skill you have, and that's that. You don't have to think about it too much after that. All right, let's do the final example that I'd like to do here, and that's finding the surface area of the torus. I believe that we've already found the volume of the torus, in fact, by 2 different methods. I think I did it myself in the lecture on cylindrical shells. I think I did this finding it by cylindrical shells, and I asked you to do it by washers, so you could, you know how to find the volume. Now we're going to find the surface area of the torus. So I'm thinking of it in this manner here. I'm going to look at the top half of the bagel or donut, however you wish, like you would slice it if you're going to put it into the toaster. That half, the top half, so I'm thinking of having that a semicircle there like that, and this is this distance here, it's capital R, and then this distance here, this littler distance is little r. Okay, that's the radius of that circle, and I'm going to revolve this thing in this manner around the y-axis, and then so this is going to there's going to be one of those over. I'm going to try to get this about halfway over. It's not symmetric. Trying to make this the same distance here. That distance, so about here. I've got my guy like that. Yeah, I'm not going to be getting a job as an art teacher anytime soon. Okay, so that is rotating around this way here, like that, and rotating around like that. Try to give that 3-dimensional. So we're taking that. It is rotating around the y-axis, and we want to know what's the surface area. So I'm taking a look at this circle here, and that circle, well, let's see what that is. That is a circle, and it is centered at the point, so the origin of that circle is r and 0. This r on the x-axis and 0 on the y-axis, and that circle has radius equal to little r. So now I can easily write out the equation for that circle, and that is x minus capital R squared plus y minus 0 squared equals r squared. That is the equation of that circle. And now I'm thinking about the top half, because the surface area, I'm not gonna consider this part of it. I'm simply gonna find the surface area of the top half and then double it using the symmetry of the situation. So y here is the square root of r squared minus x minus r squared. So that is this function right here. That is y, this y here. Okay, it's f of x. So I have the equation of that, and I'm revolving it about the x-axis. So the radius is x. I'm sorry, did I just say that? I'm revolving it about the y-axis. So the radius is x. Y-axis revolution. So radius is x. So now I can write out the integral. So now I see I have got f of x. This looking a bit nasty. It's going to take us, we have to be careful with our algebra here. There it is. So I'm going to need f prime at x squared. So I'm going to calculate f prime at x. I'm going to take the derivative with respect to x, and I'm going to get a 1, well, I'm going to get, let's see, 1/2, and then this will be, I'll have this in the denominator, r squared minus x minus r squared. Then the derivative, employing the chain rule, I'll have the derivative of the inside. That's going to be minus 2 times x minus r. Okay, so taking the derivative of f of x, getting f prime at x, then I have to square that thing. First of all, let me just cancel these things out. That'll be helpful. And I'm going to square that thing. So I'm going to get prime at x squared. That is going to be x minus r squared over r squared minus x minus r squared. Okay, and then I'm going to add 1. Really, I think the difficulty of this problem is in some sense, I mean, once you know what to do, the difficulty is not flubbing up on the algebra, which is actually, pretty easy to do. So just cautiously going here, I'm going to add 1. I'm going to add 1, which means I'm going to take 1 in the form, so that it turns like, so I'm thinking like this. 1 is equal to r squared minus x minus r squared, minus x minus r squared. And that's how I'm going to be thinking of 1. And so I have a common denominator, and I'm going to be adding 1 like this, x r squared and x minus r squared plus x minus r squared all over r squared minus x minus r squared. And I can simplify the numerator mercifully. Some things are simplifying. That cancels with that. So that's good news. So that means that this thing is r squared over r squared minus x minus r squared. Okay, so now I've got that set up. I can write out what my surface area is. It's going to look like this. It is going to be 2. That 2 is there because I'm only calculating half the problem, and then I'm doubling it. So that 2 is there for that reason. What are my limits of integration? Let's take a look, because that's a little bit tricky in this case. And that is, I see I want to integrate from here through to here. Okay, and at this point right here is what? Capital R minus little r. And then this point on the other side is capital R plus little r. And so I'm going to get those limits of integration. Then I've got my 2 pi x, my circumference, multiplied by the 2 pi x times the square root of this guy here, the arc length differential. So I'm taking the square root of that. I'm going to get r over the square root of r squared minus x minus r squared dx. Let's make that a bit neater. All right, so now I've actually, the problem in some sense is solved should I be able to integrate this thing here. So let's see what happens. I'm going to just do a little bit of simplification, just moving things around a little bit so I can see more clearly what I'm doing, and that is partially is just combining these two things. Also, this is independent of x, so I'm going to write those on the outside here, and I have the integral from r minus r to r plus r, and I have left in the inside here x dx over the square root of r squared minus x minus r squared. Okay, same thing has happened. I effectively have a x squared in the denominator. I'm seeing this is effectively an x squared, and then I see I have an x here. This leads me to the following substitution: u equals x minus r, and that means that, of course, du will be dx, and then I'm going to be very careful to check these, change these when I rewrite the integral with the substitution. So then s becomes equal to 4 pi r, and the integral now, when x is r minus r, u is minus r, and then when x is big R plus little r, u is little r. Okay, I have that dx is du. I have that x is u plus r. Okay, u is x minus r, so x is u plus r. So right here I'm saying x is u plus r. Dx is du, and then over here I have the square root of r squared minus u squared. Okay, let me just split this into two. You'll see why in a moment. 4 pi r integral from minus r to r. There's two things here. U du over the square root of r squared minus u squared. And then there's r du over the square root of r squared minus u squared du. Okay, so I've split them into two. That's just splitting this here. Okay, there's something to be seen right here, and that is that this thing right here is an odd function. And we are talking about integrating over a symmetric interval. So that thing is 0. Woohoo, right? Work saved. that always makes me happy. So this is equal to 0. I don't have to do anything else. I notice that it's an odd function. It's over a symmetric interval. So now it is 0. Okay, I'm going to have to erase this. Just give myself a little bit more space. Good news, I'm almost done. I have one integral to do, this one here. So my problem is now to integrate that, and I'm going to get, I have my, so s is going to be 4 pi r, and now I'm going to integrate this thing here. What is that? That is the arc sine. So again, you have to be able to recognize when you're seeing certain integrals. So that is going to be the arc sine of u over r evaluated at minus r and r. That is that integral right there. Okay, so that means it's going to be equal to 4 pi r like that, 4 pi r, and then I've got the inverse sine of 1 minus the inverse sine of minus 1. And that is going to be pi by 2 minus pi by 2. Okay, so and that of course is pi. So I've got 4 pi squared capital R little r. Okay, so that's surface area of a torus. This is very exciting. I mean, something that may seem hard to come up with without this kind of technique. I mean, calculus is great for this sort of thing. Surface area of a torus. Torus is 4 pi squared r. Okay, here's something for you to consider, just because it's counterintuitive and quite interesting. That is this thing. I'm going to just mention this. I'm not going to spend a bunch of time on this, but consider this situation here. We've got let's just say this is 1 right here, and this is 1 right here, and we draw this function here. Y equals 1 over x. And we're going to have this guy going right to continuing indefinitely. And what we're going to do then is we're going to take the region bounded here, this region here, bounded by x equals 1, bounded by the x-axis, and we'll keep going all the way to infinity. And then we could revolve it this way, and we would get sort of a long, very long, and a horn shape that would be extremely narrow at the end as we're heading out in this direction, right? So we get this horn shape where it looks like this, and it keeps going like that, and it's this horn. And then there's our circles are here. Okay, so we have this long skinny horn. Well, at least it's skinny at the right-hand side. Okay, so we now could, we know how to handle improper integrals, which of course this is going to happen because we're going to be using something all the way to infinity. So we can use our skill for improper integrals, play in here. We could figure out what is the volume of this thing and what is the surface area. Okay, we've all these skills we now have, the surface area. And amazingly, try it out. I mean, set up the integrals, and they're not that hard to evaluate. You can do the volume and the surface area, and you'll find out that when you do the computation, you will find out that this thing has finite volume. The integral will converge, and you'll find out that it has infinite surface area. How bizarre is that? It means that this shape that we're imagining here, that you could take it and fill it with a finite amount of paint, but you can never buy enough paint to paint the outside. Okay, this guy's called Gabriel's horn, the horn of the devil. Okay. Or I guess the horn of the archangel, really. Okay, so that is the name of this guy. It's an interesting shape with a unusual characteristic. That is our lecture on surface area of a solid of revolution. I will be back with some more exciting stuff coming shortly. Thank you.